Okay, good morning, everyone. Welcome back. Couple of housekeeping notes again before we get started. As promised, I'll always put up the schedule at the beginning of class so we can see where we've been, where we are, and where we're going. I apologize, I can see some of you squinting in the back there. This is where we are, where we've been, where we're going. Undergraduates, you're working on assignment 1. Graduate students, you're working on assignments 1 and 2. And next Monday at 11:59 p.m. for the undergrads, assignment 1 is due. For the grad students, assignments 1 and 2 are due. For those of you that have already started, and I hope most of you have, any questions? Any installation issues? Wow, great. Okay, excellent. Off you go. All right, you're running ahead a little bit of in the physics engine. We're obviously going to get to physics engines next week, possibly the week after. We'll see. So next Tuesday, when we introduce assignment 2 for the undergraduates, we're going to pause and we're going to talk about links and joints. Links are the things that are the physical objects that are going to make up your robot, and the joints are the things that connect them together, not unlike your knee joint and your elbow joint. Joints are a little bit tricky to define in the particular physics engine that we're using in this class, which is PyBullet. We've used different physics engines in previous iterations of this course. PyBullet has a lot of things going for it. The main thing PyBullet has going for it is that it has good cross-platform installation. So I'm happy to see none of you put up your hand when I asked about installation issues. We're over the biggest hump in the class, trust me. Yes?
I apologize, but it says to the attendance sheet that I no longer have access. Is it
Yep. Yeah, I'll talk about attendance sheets in a moment. So PyBullet, good for installation. Doesn't matter whether you have a Mac, a PC, or a Linux in this class. Whatever you have is perfectly fine. There's a couple of drawbacks to PyBullet. One of them is that it's a little tricky to understand how to define joints. So some of you who have moved on to trying to define joints in PyBullet, and you're scratching your head because it's a little bit confusing. You're not alone. I'll take a few minutes out of class on Tuesday and talk you through it. All good? Any other questions about the assignments? Okay, back to the attendance sheet. So I've been trying to come up with a good way to make sure that if you're sick or for some reason you can't come to class and you want to just watch the video lecture afterwards, that you can mark yourself as here, that you're still with us and keeping up with the material. The way we're going to do this as follows. At the beginning of every in-person class, I will write a new URL on the board. That's why you couldn't get access to the old attendance sheet. You're now locked out. There's a new attendance sheet. If you haven't already, feel free to get out your device, navigate to this link, tick yourself off, and then please stow your electronic devices again. If for some reason you can't come to class, I will I'll record the lecture, put it up on YouTube, and you can watch the YouTube video at any point during the day, because you need to take a quiz by 11:59 p.m. tonight. Inside that YouTube video, for a few seconds, you will see the link to the attendance sheet pop up. So again, it's a little bit of a pain in the butt, but this is a gentle prod to make sure you're watching the lectures, going and marking yourself off, and so on. Make sense? So if you're here, mark yourself off. If not, if you can't make it to class, watch the YouTube video. You'll find the link, type it in, mark yourself off that you've watched the video, go take the quiz, and you're all good. It's a little awkward. It's the best thing I've come up with so far to try and support everyone as we try to make it to class in person, but don't always make it. Sound good? Okay. I also went over a lot of other logistics about how this class is going to run last time. Any lingering questions about any of that? No? Okay, so let's dive back into evolutionary robotics. As promised, we're working our way through a few themes. We're working on an introduction at the moment. I didn't quite finish lecture one slide deck, so I'll navigate to that in a moment. We'll finish out lecture 1, and then we'll start in today on a very, very, very short history of artificial intelligence. So back to the lecture one slide deck. I was not able to show you these videos last time, but it looks like I've got better Wi-Fi for some reason today. I'm not going to show you all the videos that I missed last time. You can go and watch them for yourself. I do want to show this one, or this pair of videos, because I think it illustrates a lot of the interesting things and some of the challenges about evolutionary robotics that you will come up against as you take this class, as you implement the assignments. Okay, so as I mentioned last time, this is from an older experiment. We've got our virtual robot. It's operating in a virtual task environment. It's a pretty simple task environment. There's not much going on in there except the existence of this blue block. Inside this robot, which you can't see, is a neural network. That neural network has a whole bunch of connections that connect the sensors to the motors. So at every frame in this video, the robot is sensing something about its environment. The neural network is transforming that sensory information. The neural network is sending signals to the motors, which control the joints, which cause the robot to move. The moment the robot moves, the values arriving at its sensors change, and it senses, thinks, and acts again. Yeah? Okay. You'll notice that in this video clip, there's a series of very, very short videos. Each short video clip inside this overall clip is showing a snapshot of the evolutionary process. This is evolutionary robotics. So around our virtual robot and virtual environment, we're wrapping an evolutionary algorithm that is going to tinker with, at least in this experiment, it's going to tinker with the internal neural network of this robot. This evolutionary algorithm maintains a population of brains for this robot. The evolutionary algorithm is dropping one brain or one neural network into the robot, one after the other, and it's watching how well the robot does at whatever we want the robot to do with that particular brain. If the robot does a poor job at whatever we want the robot to do, that neural network is deleted from the population. Once the evolutionary algorithm has gone through this population of neural networks, whichever neural networks have survived, the evolutionary algorithm makes randomly modified copies of the surviving neural networks and repeats this process. What you're seeing in these short video clips is the best neural network that the evolutionary algorithm had found at that particular time. Yeah? I think I mentioned this last time, or you can probably tell by looking at this video. The fitness function, the thing that we've asked the evolutionary algorithm to evolve, is a robot that grasps the object and pulls it onto its back. Yeah? And so this process, I think I did this experiment like 15 years ago. It took about I think it was about an overnight on my laptop at that time. So I've obviously sped this up quite a bit, showing you the highlight reel. So we're sort of speeding through the evolutionary process so that you can visually see evolutionary improvement here. Is it improving? How are we doing? It's getting better, right? You can see it eventually figures out how to orchestrate the movement of its front gripper to grab the object and pull it onto its back. This is about as simple as we can get for an evolutionary robotics experiment. We're going to see dozens of them throughout this course, and they're going to get more and more complicated and intricate. But at heart, they're going to have these four components in some way. Yeah? Questions, comments? Yes?
When you say it's choosing between the different neural networks, is it doing that after every iteration of doing the whole thing, or is it doing that every frame?
Oh, good question. Okay, so the video's a little confusing. Ignore the video for a moment. In this experiment, the evolutionary algorithm starts by creating 100 random neural networks, random ways of connecting the sensors to the motors. It comes up with 100 different ways of doing that. There's an infinite number of ways, picks 100 at random, takes each neural network, drops it into the simulated robot, and basically runs the simulator. So for those of you that have got to a module B where you create an empty simulator, that's basically what it's doing. Drop the neural network in, run the simulation for 1,000 time steps in the simulation. The end of those 1,000 time steps, how is the robot done? In the simulator. Assign a number, how good it is at doing so. Yeah? Take the next neural network, drop it into the robot, run another 1,000 frames of the simulator, measure how well that neural network is. Do that for the rest of the 100 random neural networks. Delete the bad neural networks, make randomly modified copies of the surviving neural networks, rinse and repeat. Make sense? Okay, and then out of that whole process over and over and over again, I'm showing you this 8-hour process sped up. Okay, as I just mentioned, this is about as simple as you can get. I'm going to show you the second video now where we're going to make a slight change to the experiment. We're going to go back to the beginning. The evolutionary algorithm is going to start with 100 random neural networks, but now we're going to change the evolutionary process a little bit. How have we changed things in this second experiment? Sorry?
You're trying to move the block forward. Is that what you're targeting?
The blue block is moving forward. In this experiment, we added in some additional code that every time the robot evolves to grasp the object, we change the robot's environment. We make things a little bit more difficult. We move the blue block 1 millimeter further away from the robot. Let me start this over again. When we change the robot's environment, whatever was good before, the neural network that allowed the robot to grab the object and lift it onto its back, when that neural network runs again, it might fumble the block because the block is a little bit further away. So evolution has to sort of retune the neural networks to this new environment. Again, rinse and repeat. Make sense? What's happening? What is this evolutionary algorithm's response to the fact that we keep making the environment slightly more difficult every time it evolves a solution to the current problem?
It's learning how to walk.
It's learning how to walk, yeah. In the fitness function, the thing that we gave the computer to measure how good the robot is, that fitness function said nothing about walking. All we said is, evolve a robot that grasps the object and lifts it onto its back. Yeah? Grabbing and lifting the object onto its back, that's a result of direct selection pressure. We're going to introduce a lot of terminology from evolutionary biology in this course. We are directly selecting for object manipulation. In retrospect, watching this video, we were also indirectly selecting for locomotion. We didn't explicitly ask for that. We're getting it as a side effect. Yeah? What else is happening here? There's a lot going on in this video. Imagine you're a biologist out in the field and you're observing this evolved species. You're sort of acting as natural historians here. What's happening? It's using the pincers to balance itself. We might think, if you look at this robot, okay, it's got pincers which it's going to use for object manipulation, and it's got legs. It's going to use those for locomotion. That seems obvious. Arms for manipulating things, legs for getting from point A to point B. Evolution doesn't care about our assumptions about how things should be. For whatever reason, in this case, evolution found it useful to actually use the motion of the gripper for locomotion. You'll notice that the motion of the gripper is actually moving in phase with the motion of the legs. What else?
I could be totally wrong about this, but it seems to me like it's also sort of using the grippers and the front of its body to feel around for where the block is so it knows when to grab it?
Maybe, yep. So I mentioned that this robot senses its environment. It has touch sensors in the tip of its pincers, so in the same way that you can feel a lot in your fingertips. So it can feel for things. Maybe it's actually looking for the object somehow. It's kind of hard to tell from this video, but maybe that's part of the solution evolution has hit on here. What else is going on?
It's like generally getting quicker. It's like walking and picking it up.
It seems to be getting a little bit better over time. There's a subfield in machine learning known as meta learning. As the name implies, this is about trying to teach a machine not just to learn, but to learn how to learn. This course is not focused on learning, it's focusing on evolution, but you see that in evolution as well. Things evolve to get better at evolving. You often see in natural species and also in robotics that this evolutionary process starts to get better over time. What else is going on? We evolved this robot to grasp the object and lift it onto its back. Is it optimal? Is this the best solution? Would you deploy this in your warehouse if you were a client? Why not?
The rectangle gets like shifted around a lot, like jostled.
Gets jostled around a lot? Yep.
After it puts it on its back, it drops a lot of times.
There's a lot of fumbling. If the evolutionary algorithm could speak, it would say, what's the problem? You said grasp the object and lift it onto my back. It's exactly what I'm doing. You didn't say, and keep it on my back and make sure it doesn't roll off and make sure it doesn't jostle around too much. I did exactly what you asked me to do. I apologize if I already used this joke last time. Evolved robots are often like teenagers. They'll do exactly what you told them to do, but they'll do it in every way that you, in retrospect, didn't want them to do it. That's not what I meant. You know that's not what I meant, but I did what you said. This is known in evolutionary robotics and a lot of other branches of AI as perverse instantiation. In this case, our robot is instantiating the behavior we want. It comes up with a solution to the problem, but it's doing it perversely. In retrospect, when the human observer sees what the AI has come up with in this case, we realize that's not what we wanted. Perverse instantiation, you'll see lots of examples of this throughout the course. When you start evolving your own robots, you're going to see firsthand examples of perverse instantiation. Shows up all over AI. What are some other examples of perverse instantiation from some of the other branches of AI?
Maybe Microsoft's Tay robot that they put on Twitter.
Absolutely. Yep. You teach a machine language, and the first thing it will typically learn is swear words and every racial slur, every bias that exists, because unfortunately it's learning from humans. Yep. Other examples?
Like social media algorithms pushing like super like narratives and articles and stuff that inflame people rather than bring them together.
Absolutely, right? You want to keep eyes glued on Twitter. What's the best way to do that? Maybe not truth and beauty and light and all the rest of it. Other examples?
I think there have been some instances of police using like crime prediction algorithms that like end up targeting minorities.
True. Yep. Great example. Obviously, bias is still a massive problem in AI. Good example about a certain institution, the police using it, might be human error in that case, right? Here, we can claim we're a little bit innocent. We asked for something, we didn't get what we wanted. You can obviously, consciously as a human user, use something for not such a great purpose.
Maybe spam filters blocking out real emails just because they have certain words in them.
Yep, I think that would count. We figured out autonomous cars. Why aren't there any autonomous cars here? What's the problem? It's a solved problem, right? Where are all the autonomous cars? Why did I have to drive myself to work this morning? Several examples of perverse instantiation with autonomous cars.
Sometimes they'll like brake in the middle of the highway if it sees an obstacle.
Absolutely. Wasn't there, I think it was last week, Tesla decided to just slam on the brakes in a tunnel somewhere for whatever reason. It probably thought it was doing the right thing. It just maybe didn't have the larger context of what was going on. So in this course, you're going to see a lot of, hilarious fails. In a real world with deployment AI, it is not a laughing matter. It is a matter of millions or billions of dollars, and in a lot of cases, human life and limb. It is an unsolved problem in every branch of AI. It is the thing that's holding out larger outrolls of AI into everyday society. As you're working through evolving your robots and you come up with good solutions to perverse instantiation, I and my colleagues would love to hear from you. It is probably the underlying open problem in AI and robotics. Okay. Question.
Sorry, could you just give another definition for that?
For perverse instantiation, it instantiates exactly what we asked it to do. Pick up the block and lift it onto its back. But it does it perversely, and the perverse in this case means that a human observer in retrospect, meaning after the machine has learned or evolved to do whatever we want it to do, in retrospect, most humans agree that's not the way it should be done. Perverse instantiation. Yeah. Autonomous Teslas most of the time work pretty well, but most people would agree that slamming on the brakes under the bridge, whatever the details of that example were, the Tesla car probably had a good reason for why it slammed on the brakes, but most humans who had a larger view of the car, the lane, the highway, the tunnel, whatever was happening on either sides of the tunnel, would agree that wasn't the right solution in retrospect. That's perverse instantiation. Yeah. Okay. Okay, so I just wanted to make sure we saw that video. Let's skip ahead. Where did we get to last time? We got to talking about the submission process. This is what you're going to be building over 10 weeks or 5 weeks. You're starting to install and play around with the empty simulator. Okay. And then as I mentioned last time, you've got 4 weeks or 9 weeks to come up with a project of your own. A big question you're going to struggle with at that time is, what's a good project for you? What's too easy? What's too hard? Here's a couple of examples of things you can try. There's also more examples in the subreddit. Given the same optimizer, given the same evolutionary algorithm, the same neural network that you programmed up over these 10 weeks or 5 weeks, and running the evolutionary algorithm for 8 hours overnight on your laptop, can you get a 4-legged robot to evolve to walk further than a 6-legged robot or not? So you get to the end of the 10 weeks, you're going to have at that point a quadruped, not that different from the one you just saw. You spend the next week adding 2 legs to it. So now you can run your code in 2 modes. You can evolve brains for a 4-legged robot, or you can evolve brains for a 6-legged robot. After you've implemented the 6-legged robot that night, you evolve brains for your 4-legged robot for 8 hours, and you see how fast the 4-legged robot moves the following morning. The next night, you run the other version of your code where you evolve brains for the 6-legged robot and see how fast the 6-legged robot moves the next morning. Third night, you again evolve for the quadruped. Fourth night, hexapod, quad hex, quad hex, quad hex. You start to build up this data set over the remaining week or 2 of the class. And during the exam period, you come to class, you show us videos of your evolved quadruped, like I just showed you, and videos of your hexapod, and we see what the answer is. Which moves faster? Which do you think in this thought experiment? Lots of examples of 4-legged animals and 6-legged animals out there. Which is going to evolve to move faster?
I think the 4-legged one will, because you'll have less that needs to optimize.
Great question, right? So one point in favor of quadrupeds is there's less material to optimize. If you think about connecting the sensors to the motors of a quadruped, there's much less connectivity there that needs to be figured out. If you're going to connect the sensors in a hexapod to all the motors and all 6 legs, there's more stuff that evolution has to optimize, so it's going to take it longer. Okay?
I think the hexapod might be faster because it's easier to balance on 6 legs.
Balance is a big part of moving legged locomotion. We're going to talk about legged locomotion next month. So there's a lot of biomechanical arguments you can make in favor of a hexapod. So we've got one thing that might help out the quadrupeds, one aspect that might help out the hexapods. It's hard to know. Let's run the experiment and find out, right? Okay. You can change what you ask the evolutionary algorithm to evolve. You can change the fitness function. You can ask it not just to evolve fast motion. You could ask it to evolve a way of moving for your quadruped in a particular way: walking, trotting, cantering, galloping, pronking, Any horse people here? There's one horse gate that's missing from here. No? No horse people here? I've got cantering on here. There's an Icelandic horse that is capable of a 6th quadrupedal gait. You can YouTube it after class. Okay. You can also change your fitness function to select from more than one thing. So in the programming projects, you're going to assign one number to your robot, how many meters it travels in 1,000 frames of the simulation, one number. You can also assign multiple numbers to a robot, which is how fast it travels and how much energy it needs to do so. Yeah? Again, when we talk about legged locomotion, locomotion is tricky because for all of us, we're optimizing not just one thing, how quickly you can get to class on your legs. It's how much energy you require to do so, and a bunch of other things. So you can explore what's known as multi-objective optimization. Multi-objective optimization. We'll talk about this later in the class as well, where you're going to evolve things to be good at multiple objectives, multiple traits. Yeah? Okay. You can stick a laser rangefinder on your robot, put some additional objects in the environment, evolve the robot to classify or categorize things, evolve the ability to walk towards round objects, but away from rectangular objects, for example. Yeah? Some of you may be wondering what locomotion has to do with AI or intelligence in general. Locomotion is a stepping stone or a step towards, no pun intended, more cognitive abilities. Yeah? One of them is being able to categorize friend from foe, poison from food, mate from enemy, so on. Yeah? Okay. There's also some links down here for some of the projects that have been done in previous years. Let's see if this will run. Oops, that's not what I want. In all of these videos from 2 years ago, on the left, you'll see examples of random neural networks, and then after evolution, the evolved neural network. And hopefully in most of these, you can figure out what it is that the robot was evolved to do. This one might be a little bit difficult to see in the back of the room. What you're going to see in a moment in the right video, the robot is carrying an object on its back and not dropping it. There's actually 2 videos here, so they're showing 2 different evolved solutions. One of the nice things about evolutionary algorithms, it doesn't give you just one solution. It gives you a portfolio of diverse solutions. You can try climbing. Climbing is really tricky. These are random neural networks. Here's an evolved neural network. I don't know if that counts as perverse instantiation. Stair climbing seems a lot easier. Turns out it's often not as easy as it seems, but doable. That's bipedal locomotion, right? Perfect. Maybe not. Same project, different body plan. A little bit better. It's an example of sensor motor coordination. A lot of humans aren't very good at this task. Okay. Just a sort of sample of the sorts of things that are doable and reasonable in this class. Yes?
What do you think the answer number 1 is? Or what's the answer?
I am not going to say. We will see. Let's see if some of you can come up with an answer. The answer is usually always, it depends. So it doesn't specify here what exactly the quadruped looks like. You just saw several different kinds of quadrupeds. Obviously, you can make lots of different kinds of hexapods. Many of you might tackle this project. If you do, you will all probably come up with slightly different kinds of quadrupeds and hexapods, and we might get different answers for some of the reasons that were already mentioned. Yeah. Okay. Okay, so we talked a little bit last time about why you might be here. Why might we want to actually build robots? They could be useful. They could be useful in a lot of outdoor everyday environments. They could bring down the cost of manufacturing buildings and bridges and outdoor infrastructure. We talked about some of the intellectual motivations for wanting to build robots. They might be used as, they are used as scientific tools to try and understand the nature of intelligence in general. Yeah. We're going to talk a little bit now about why we might want to use evolutionary approaches to create our robots. Robotics is a massive field. There's lots of different attempts underway to try and make smart machines that operate in the real world. What are some of the advantages of evolving robots rather than endowing them with the ability to learn? One reason we want to use evolutionary robotics is making a controller or a neural network or a brain for the robot is not an intuitive process. So however we're going to get our robots to do whatever it is we want them to do, it's probably not going to be a human programmer saying, if you sense this, then do that. If you sense that, then do this, and so on and so forth. It's not just non-intuitive, it's super, super, super non-intuitive. And here's an example. I'll give you a sense of how non-intuitive this problem is. What the GIF you're seeing in the upper right, that's known as a Stewart platform. As you can see, it's kind of an interesting mechanism that comes from mechanical engineering. You'll notice that there are these two circular plates, and these two plates are attached to one another with 6 pistons. You can only see 5 in the GIF, but there's 6 there. As you can see, these pistons elongate and shorten their length, and they're attached. Each piston is attached to the plate with a universal joint, which we'll get to when we get to joints in the programming assignments. But the joint here is basically acting like your shoulder joint. It allows this kind of rotation and this kind of rotation. So if you watch those joints, you can see they're doing something like this. Yeah? Okay. When I was still working at Cornell a while back, I was working with a mechanical engineer, and we made a robot which we nicknamed the nonaped for a 9-legged robot. We took 2 of these Stewart platforms, turned them on their side, and attached them end to end, as you can see in the lower left image. So we've got 2 Stewart platforms, which means we have a total of 12 pistons. And we attach these carbon fiber legs to them. The legs don't actually do anything. They're just kind of there to allow this thing to move around, which I'll show you in the lower right in a moment. Before I show you the video, I want you to imagine that I task you not with evolving a brain for this robot or giving this robot the ability to learn or improve its own brain. You're going to program its brain yourself. Yeah? We've got 12 pistons. I want you to imagine that at every second, you are allowed to send one of 2 commands to each of the 12 pistons: shorten or elongate. -1 for shorten, and elongate for, and +1 for elongate. So good, so far so good? So at every second, you're going to determine which 12 numbers, which 12 binary numbers to send to the 12 pistons. Second 1, second 2, second 3, second 4. And you're going to do this for, let's say, 30 seconds. So what you're really programming is just a matrix that has 12 rows in it, 1 row for each of the 12 pistons, and what did I say, 30 seconds? So 30 columns of binary numbers. You're going to basically write down a binary matrix, and this binary matrix, when sent to the robot, should cause it to move from the left to the right here. Go. Obviously, this is a cooked example, not so easy to do. Maybe there are some general strategies here. Any ideas? Probably hard to come up with the actual numbers, but maybe you could think of a general strategy and then boil that down to binary numbers.
You could kind of get it to move like an inchworm, maybe.
All right, so there's a little bit of a hint here. You can see in this case it's sort of cinched up its waist. So maybe you get it to move like an inchworm. I want you to look at the GIF again and try and figure out what 12 numbers you need to send to cause this thing even not just to move as an inchworm, but to assume this static pose, to pull in and up at its waist and leave its front and back on the ground. I'm not a mechanical engineer, but I tried to sit down with pen and paper and figure this out. I couldn't do it. Not so easy to do. Yeah? Wouldn't it be easier if we could just get a computer to do this, which is exactly what we did in this particular project. So what you're going to see in a moment is we made a couple of matrices, of these binary matrices, and we sent them to the robot just to kind of see what would happen. We didn't see much correspondence between what we wrote down and what we sent to the robot. Here's a couple of random matrices. Here is one, at least we could figure out what it would cause the robot to do. So we started to figure out a little bit about how to get this thing to stretch and contort. But getting it to move forward, that was at the edge of our intuition. So we started to get something that kind of worked. Evolution came up with this. We didn't say anything about moving face first, right? Perverse instantiation. There's another evolved matrix. There's evolution showing off. It can go in the other direction. You'll notice that it's how, question.
So you tried to do it like pen and paper first, and then you gave it to an algorithm?
That's it, yep. So the last 20 seconds there you saw, those were the evolved solutions, which were way better than anything we could come up with, yeah. You can see that it's in this sort of wooden cage, and sort of we put up some plexiglass when it was actually working. The thing that's driving the pistons is compressed air. We took a compressed air canister out of one of these paintball guns, and basically modified it in a way we weren't supposed to. At one point, one of the parts flew off and embedded itself in a cinder block about 3 inches deep. So we dodged the bullet, literally, in that case. Okay, that's real-world robotics for you. Okay, so the point I was hoping to make here, before I got sidetracked, was it's not intuitive, not so easy to manually tell a robot what to do. Yeah. So in most of robotics today, pretty much 100% of all robotics, it's AI in some way. The human tells the AI, we want a robot to do X, and the AI tries to figure out how to get the robot to do X. The AI usually comes up with something close to X, but not quite. That's kind of where we are these days. Okay. Another reason why we might want to use evolution rather than other kinds of machine learning is that evolutionary algorithms running in a computer, like biological evolution, have tuned not just the brains, but also the body plans of organisms together. I mentioned this last time. I'm going to come back to this a few times. Most machine learning algorithms, as the name implies, they focus on learning changes to the brain, not the body. The assumption in evolutionary robotics is that if we want a machine that's useful and safe, we need to get not just the brain right, the way it transforms sensation into action, we also need to get the body right. How to do that, we're still not quite sure. Here's a very early example of me trying to evolve bodies and brains of robots. Comes up with some sort of odd solutions. In this case, it came up with a bilaterally symmetric robot. The left side of the robot looks like the right side of the robot, which is great, but it didn't go anywhere, so evolution eventually throws away that solution and came up with this crazy solution that works. I don't know why. I still don't know why. I've been looking at this video for 20 years. I don't understand it. Okay. It's not perfect. It walks in a curve, presumably because it's not bilaterally symmetric. Who knows? Okay. So as I just mentioned, evolution it doesn't focus on one part of the organism or one part of the robot. This is my potted history of AI from the end of the Second World War until about 2006. So whatever that was, 60, 65 years. People in AI were figuring out how to tune the weights of synapses, so the strengths of connections inside of an artificial neural network. But humans programmed everything else. We decided how many neurons, how many synapses or connections between those neurons. Humans decided on the neural architecture. For most of that time, they weren't even thinking about bodies at all. There were no bodies, just the neural network. We basically solved this problem. People are now working on the architecture search problem, which is what's the right neural architecture for a neural network to do whatever we want the neural network to do. That's a hard problem. In this course and in robotics, we're trying to answer a question even beyond that, which is what's the right body and neural architecture for a robot to do whatever we want it to do. Yeah? NASA can't seem to make up their mind about whether they want to send wheeled rovers to moons in the outer solar system. Do we want to send drones? Do we maybe want to send legged robots, snake robots? What's the right body for the job? NASA doesn't know. We don't know. For pretty much everything we'd want robots to do here on Earth, same thing holds. It seems obvious at first glance that we might know what body makes sense. The humanoid body, something that looks like a dog. Maybe these things make sense because we got a lot of those in our everyday lives, but maybe not. Another good reason to use evolutionary robotics is evolution has already produced one thing that's capable of human-level intelligence: humans. So we have an existence proof that it's possible. An evolutionary process, given enough time and resources, can create some pretty intelligent machines. We're not perfect, but we're okay. Yeah? So if evolution can do it, maybe we can get evolution to do it again, just with different materials. Fourth and final reason why we might want to use evolutionary algorithms rather than learning algorithms is that most learning algorithms require detailed supervision, meaning that the neural network does something, and then the human instructor said, you made a mistake at this place at this point in time. That's the supervision. Yeah? So a neural network is learning to categorize cats and dogs. It's given a picture of a cat and it's shown and it thinks it's a dog. We actually reach in, or code that we write reaches in and says, not only you made a mistake, this was supposed to be a cat, not a dog, but we actually point to where in the neural network it made a mistake. We're giving it supervision. Yeah? Here's another biped. I also had a crack at this when I was a graduate student. This is about as far as I could get my robot to go. This biped is controlled by a neural network, but let's imagine it's controlled by this binary matrix, like we talked about in the case of the nonaped. This thing eventually falls over, but the reason it fell over was because probably something was wrong in the controller half a second, or maybe even 2 seconds into the past. We don't know. It's next to impossible to see this video, to see this thing fall over and say, that motor at 2.7 seconds, you should have been extending your leg, not retracting your leg. It's very difficult to go back and know where things went wrong. Biological evolution and an evolutionary algorithm is what's known as a semi-supervised algorithm. It's supervised in the sense that the evolutionary algorithm says this particular robot traveled 2.7 meters. So it's giving back a number about how good the controller inside this robot did. So that's a bit of supervision, but it's semi-supervised in the sense that that's all the evolutionary algorithm gets. It's just, it traveled 2.7 meters. This neural network caused that robot to travel 1.4 meters, and that one No meters at all. It fell over immediately. The evolutionary algorithm has to figure out and tinker with the internals to try and figure out what went wrong. Make sense? Okay. Okay. Took us a while to get through the first slide deck, so to reward ourselves, I'll show you what used to be the state of the art in 2013. These are actually some computer graphics researchers that use this approach to evolve bodies and brains. You can see the body evolving here, and the brain. One of the nice things about evolving bodies and brains is you can then take that solution and drop it into different bodies, and in some cases, it'll keep working. Or very, very different bodies. You'll notice the tail is helping here in the case of bipedal locomotion. This is a type of evolutionary algorithm. A nice visualization so you can see evolutionary progress here. Same thing, evolving populations of these things, deleting the ones that don't do a very good job, and making randomly modified copies of the ones that survive. Okay, I'm going to speed this up a little bit. You can watch the full video afterwards. When this was released on social media, everybody commented that this is how they feel on Monday morning. Okay. Okay. Any questions about that before we switch to our potted history of AI? Okay. All right, as promised, this is going to be a very short overview of the history of AI. Like most histories, we're going to do this in chronological order. How far back are we going?
Whole 30 years.
More than 30 years. If there's Latin involved, you know we're going back. We're actually, this is the history of AI. The history of evolutionary robotics didn't start until the mid-90s. This is the history of AI. Where in time are we? When are we?
Renaissance.
Who said this?
René Descartes.
Absolutely, right? So we're going to start our history. We could start anywhere, I guess. We're going to start in the 1600s in this case with René Descartes, cogito ergo sum, or je pense donc je suis. He liked to write in French. He liked to be a member of the common man rather than writing for the elites. I think, therefore I am. Obviously, a beautiful, subtle argument that we could spend the whole course dissecting. Apologies to René and to everyone here. We're going to do this very, very quickly. What can I trust? What's actually out there? Maybe I, René, am actually in the matrix and nothing really that I see or anything I sense is actually real. Someone or something is trying to play a trick on me. How do I know what's real? Do I even exist? This is a question. I'm René and I'm asking this question. There's something that's asking the question. I don't know much about this thing. I don't know I don't know whether anyone else is out there. I don't know whether anything is out there. I don't even know whether this thing is real. But somewhere inside, there is something that's asking this question. Whatever that thing is, which in English we use the term I for, that thing exists. Something must be asking the question. That's the only thing, according to Descartes, that he could trust is real, that exists. It's hard to imagine an evil god or an evil demon or machines that would be able to trick you to such an extent that you think you exist when you actually don't. It just sort of is an ill-posed question. Something's got to be in there asking the question. For Rene, he came to the conclusion, therefore, that this thing exists. For him, as a religious person, it was a soul. Today, if you're not religious, but you sort of agree with his argumentation, you might say the mind exists. For Descartes, beyond that, all bets are off. Everything else could be an illusion. So for Rene, then, there are two different kinds of things in the universe. Res cogitans, or for Rene, this was the soul or the mind, and then physical stuff. They're very, very different. And over the decades and centuries, this has permeated pretty much all of Western thought. It has a lot of different names. It's usually known as Cartesian dualism or the mind-body problem. These things are different, and it's problematic that they're different. Why is it a problem? Who cares? Mind and body are different. We're done. Let's move on. How do these things talk to one another? If one of these things is non-physical, is immaterial, and the other thing, body, is physical, what does an interface between an immaterial and a material thing look like? People have been trying to figure this out for a very long time. Yeah? Why are we talking about Cartesian dualism in a class on AI and robotics? Seems like kind of an odd place to start. Any ideas?
It kind of feels like the difference between the neural network and the actual body of a robot.
We have two fields, AI and robotics. And they're divided based on whether they believe the body, which already is assumed to be a different thing from whatever is in here, matters or it doesn't. Cartesian dualism permeates all Western thinking, pretty much all Western thinking, including robotics and AI. It actually set, maybe unbeknownst to the pioneers of these fields, it set the structure of these two fields. It created these two camps, which are often at war with one another, and we'll see examples of that as we go. Yeah? So we're not always aware of it, but Descartes is there, this distinction. When we get to the biobots and some very recent findings in biology, biology suggests, as biology often does, that this distinction is a human distinction. It's something we made up, but it's not real. Evolution does not see things this way. Evolution doesn't distinguish between body and brain, doesn't even consider them different things. We'll get to that. Okay, we're going to jump 299 years ahead. I promised you this was a potted history, so we're jumping over a lot of interesting things to 1936. The years leading up to the Second World War, and Alan Turing. Hopefully he needs no introduction in this class. Alan Turing, famous for a lot of things. One thing is the Turing machine. Simplest explanation of a Turing machine: takes an input, does some internal processing, and then provides some output. We can be a little bit more specific about the Turing machine. We can describe in a couple sentences. Anybody want to take a stab at it? Turing machine doesn't exist in a vacuum. It's got an environment, which is this tape made up of a bunch of these panels. What does the Turing machine do with the tape?
It reads what's on the tape and then moves left or right.
It can read what's on the tape, so that is the input to a Turing machine. It reads symbols at the current location on the tape. That's the input. It then takes that information inside, and it might combine it with some current state, some internal state. So it's taking stuff from outside and mixing it with stuff inside. It updates its internal state, so there's an internal change. And then there are two types of outputs. It can erase the current symbol and replace it with a new one. Does it help if I do this? Can people see that in the back any better? Okay. Actually, this might help. It reads the symbol at the current, the output, writes a symbol onto the tape, and then it either moves the tape forward or back, or it moves itself. Doesn't really matter. It's just got to move relative to the tape. Yeah. I apologize for those in the back if you can't see. It'll be in the YouTube video afterwards. Okay. Again, a historical contribution here. It kind of sets our thinking about us, about organisms. We sense the world, we think about it, and then we act. Same thing with computers. We've built all of our machines around this idea. The machine takes some input, does some internal processing, and then produces output. You can probably guess where I'm going with this. Mother Nature says, what are you talking about? That's not how organisms work. They work differently. How differently? If it's not sense, think, act, what else can it possibly be?
It's like involuntary reactions.
Involuntary reactions, okay, sometimes you might do something without sensing it. Your body might sense it, otherwise you wouldn't be reacting to it. Your conscious mind or conscious brain might not be sensing it. So yeah, okay, that maybe counts. The subconscious, instincts, reflex. Yes?
You might be acting on something that's not like coming from your environment.
Absolutely, right? So you may be closing your eyes and trying to shut out everything that's happening here and now, and then act based on something you remember or something from your past. Yep, that's an option. Again, as we'll see as we move through this course, it turns out that there are even more unorthodox or exotic forms that this can take. If you think about this loop, sense, think, act, another way you can think about it is act on the world, see what the world throws back at you. So you act first, push against the world, see what the world throws back, and think about the sensory repercussions of your actions. So act first, sense after, think about that, and then act. So act first, sense after. Of course it makes sense because it's a continuous loop. It's harder for most of us to think in that way. It feels easier to think, I see something, I think about it, I do something, right? John Dewey, everything on UVM's campus is named Dewey something, Dewey Hall, Dewey Room, Dewey Staircase, right? John Dewey came up with the idea 100 years ago, I should include it on this slide, that that's a better way to think about what organisms are doing. They act first and think about the sensory repercussions of their actions. It was one of the things that made John Dewey so famous. If you don't know, John Dewey is buried right here on campus. There is a gravestone on campus. As you're walking around a campus, keep a lookout for the grave of John Dewey. Okay, let's jump forward another 20 years to 1956. And just down the road from us here in New Hampshire at Dartmouth College back in 1956. In the spring of 1956, 10 men, this is the 1950s, wrote a proposal to the government saying, please give us a little bit of money and we'll spend the summer doing the following. We're going to create this new thing, which we're going to call artificial intelligence. This was the first time the word was actually used. It was used in this proposal submitted to the government in the spring of 1956. Here's an excerpt. We propose that a 2-month, 10-man study, what a coincidence. The 10 men that wrote the proposal were the ones that were going to actually study the problem and solve it, of artificial intelligence should be carried out this coming summer at Dartmouth. And our study is going to proceed on the following assumption. Every aspect of learning or any other feature of intelligence can in principle be so precisely described that we can write it down, then turn that written description into code and get a machine to simulate it. That was the proposal. We'll do this to make machines use language, form abstractions and concepts, solve the kinds of problems that now only humans can do. Oh, and also, by the way, we'll get these machines to learn and improve themselves. We think that we can make a significant advance in one or more of these problems if a carefully selected group of scientists work on it together for a summer. Sounds reasonable? How did they do? Looking back 67 years later. Did they solve it in 2 months? 2 years? 20 years? One of the things we'll learn in this course, you'll learn firsthand, is a lot of things in AI and robotics, they kind of seem easy. Getting a robot to walk without falling over, that should take me about 14 weeks in an undergraduate class on evolutionary robotics. A lot of things are harder than they seem in AI. Why do you think that is? There's this huge underlying cognitive bias that's existed going back to the 30s, actually, about AI and robotics. We can make intelligent machines. It's not that hard.
Because we see examples of it all day in biology, so we're like, it's got to be easy.
It's got to be easy, right? There's a whole bunch of bipeds here. I haven't seen any of you fall over yet, right? It took you 20, 30 years or however old you are to get to master it. Can't be that hard. Okay, maybe not 2 months, but there you go, right? Bipedal locomotion, it feels effortless. It's easy. I recognize a lot of familiar faces. I'm doing it instantaneously. I know you, I know you, I know you, I know you. If I can do it so fast, I'm not even out of breath. It must be super easy. It's not. A lot of things that seem easy to us turn out to be very, very hard. And a lot of the things that seem really, really hard to us, in retrospect, have turned out to be really easy for machines. Like what? What's hard for us and easy for machines?
Big math problems.
Big math problems, yeah. Chess. They didn't solve it in 2 months, but chess was one of the first things to fall. Tic-tac-toe, then checkers, then chess. Took a little bit longer for Go. What was that, 10, 15 years ago? Yeah. Kind of odd in retrospect. When you think about the history of AI, we're not just wrong or we're not just sure about what we're doing. It's our intuitions are backwards. Everything we think is hard is easy, and everything we think is easy is hard. And again, we can see why we think that, but why is legged locomotion so hard and chess so easy? When we think about those more specific questions, then we start to get into the meat of what remains to be done to make intelligent machines. Yeah? Okay. Here are the 10 men who attempted to create the first AI. Anybody recognize any names on this list? Yep, Alan Newell wrote the textbook on AI, or one of the early textbooks, a big pioneer in AI.
Is that Claude Shannon of Shannon Entropy?
Absolutely. So if you've ever studied entropy or information, we live in the information age. There is a formal technical definition for what information is. Shannon wrote that definition down and defended it in his master's thesis. Yeah. And he became the father, pioneer of information theory. There was an economist involved, Herbert Simon, who actually made a lot of contributions to AI. I don't know if any of you here have taken a class with Professor Skalka here in the CS department. Professor Skalka was Herb's very last doctoral student before retirement. John McCarthy, he was the organizer. He's the one who actually invented the term AI. Marvin Minsky, a big player in the early days of AI. He co-founded MECA, the MIT AI lab. Next time you're in Cambridge, Massachusetts, go check out the Stata Center. This is where the AI lab works. This is where a lot of the early work in AI was done. Still sort of a hub for all things AI. Unfortunately, Marvin Minsky was involved with Jeffrey Epstein. Complicated history there for those of you who are interested in the people that populated the early days of AI. Okay. All right, let's keep moving forward in our history of AI here. So there were early attempts that turned out to be hard. What were some of the early goals of AI researchers? As we just saw, some of them wanted to simulate intelligent behavior. But why? Why did they want to simulate intelligent behavior? Some of them wanted to do so to understand biological intelligence. I already mentioned this. Robotics and AI is often a mirror back to us, challenging us to make sure we understand what we mean by intelligence. If we can create intelligent machines, intelligent neural networks, intelligent robots, intelligent biobots, we start to get a larger and larger portfolio of things that act intelligently. We have a whole bunch of examples from nature, but despite the diversity of examples of intelligence you see in nature, we all share a common ancestor. So we're all kind of all organisms are using some variation of very early hacks that Mother Nature discovered about how to survive and thrive in the real world. If we can create new trees of life or new examples of intelligence that have very, very different bodies and brains from anything we see in biology, we have a more diverse portfolio, and we might be able to look across organisms and machines and spot common patterns and distill those common patterns out to give us a general principle of intelligence. We don't have that yet. I mentioned this on Tuesday. We don't have the periodic table or natural selection or quantum or Newtonian mechanics. We have no foundation for understanding intelligence. One way to do that, make a whole bunch of different things that act intelligently, see what's common across them, and pull out abstract principles. Yeah. And then again, now that we understand intelligence better, we might be able to turn around and make ever more intelligent, safer, useful, general purpose machines. It's all still in the future. Hopefully some of you will come and join us on that adventure. Okay. Understanding biological systems. Here's a simple example of trying to instantiate or build into a machine principles of biological evolution. We're going to look at a very simple example of something from nature. It's a very simple behavior, phototaxis, meaning turn towards the light. I don't know if any of you had Lego Mindstorms as a kid. You can sort of build these things. It takes, an hour, 2 hours, not that difficult. Here's an example of photophobia, fear of the light. If any of you live in student housing, you'll know about this little insect known as a cockroach. You turn on the lights, it runs away from the light. They are not reprogramming their robot, they're changing its body. And now you get photophilia, the love of light, or phototaxis, going towards the light. Okay. Turns out that that's actually pretty simple. You can do that with 2 sensors, 2 motors, and 2 wires. We'll talk about that in a moment. Phototaxis is actually not that difficult. Legged locomotion, difficult. Okay. So that was just sort of a simple example of actually going the other way, taking something from biology and building it into machines. Okay, jumping from the 1950s to the 1960s, people started to create these things called chatbot. This was arguably the first chatbot. People seen Eliza before? There's probably, if you Google it, I'm sure there's a version of Eliza somewhere on the net. It was pitched as a psychotherapist. You could tell Eliza all your problems, and it would empathize, give some advice, maybe give you some pointers to things to think about. Sound familiar? Anybody played around with ChatGPT? Can get it to act like a psychotherapist? Yeah. Eliza was not based on a neural network. There was a huge if, then, else set of statements inside. If the user says, I, verb, proper noun, I hate Bill, Eliza would take the verb hate and the proper noun Bill and switch them. Why do you hate Bill? Genius. Great, right? Rule number 1 of therapy. If someone asks you a question or makes a statement, always ask a question in response. People spent hundreds, if not thousands of hours pouring their hearts out to Eliza. People were stunned in the 60s. This was it. It didn't end up taking 2 months. It ended up taking a decade, but this was it. We were near the end point. We now had a machine that could not only play a good game of checkers, they hadn't solved chess at this point, but it could empathize with people. This was the Holy Grail. We're almost done. What happened? Well, we weren't done. We are different. When you sit with a friend and your friend says, I hate Bill, you might say, why? Why do you hate Bill? But you're not just a set of if, then, else statements, right? You're different. How? You have emotions. It's obvious. We have emotions. That's the difference. Maybe. Okay. All right. This is a little bit out of order. We mentioned the Turing machine already. Going back to the 50s for a moment, Turing also invented the Turing test. It seemed that Eliza was passing the Turing test. A lot of people thought there was actually a person named Eliza that was sitting at some other terminal talking to them. They thought they were talking to a human. Turing had proposed the Turing test back in the 50s as a way to tell whether a machine was intelligent. Yeah? If a machine can fool enough people that it's a person, not a machine, that's it. That's the definition of intelligence. Yeah? We don't know really what's different between us and Eliza or between us and ChatGPT. We may never know. The best we might ever be able to do is an empirical test. If people can't tell the difference, that's it. That's intelligence. Yeah? In Blade Runner, this test is referred to as the Voight-Kampff test. In the interest of time, I won't play this clip. If there's any Blade Runner fans here, what happens at the end of this test? Doesn't go so well for the person administering the test. Optional homework, but highly, highly recommended homework. If you have not seen Blade Runner, go see it. It will help you with this course immensely. Okay. All right, moving on to the 1980s. A lot of people had a problem with the Turing test and Eliza. They said, no, we're starting to go down the wrong path. Just because something fools us into thinking it's intelligent does not mean it's intelligent or that it's thinking. We are humans, we are different. We are not faking intelligence, we are intelligence. Turing and people that agreed with Turing pushed back and said, prove it. The best proof, if you like, at that time, and arguably still today, is known as the Chinese room problem. This was formulated by John Searle. Anybody heard about the Chinese room problem before? Couple people. Okay, all right. So here we go. We take a person, an English speaker, speaks no Mandarin, no Chinese. We lock them in this room. You can see this room has a door and there is a slot in the door. There are some Mandarin speakers outside the door. They write a question in Chinese, and then they pass their question written on paper through the slot to the person inside. This person inside doesn't speak Chinese, so they see a whole bunch of squiggly markings. They take the first squiggly marking and they go to this massive lookup table. They go to this massive book, which is basically a dictionary. It's a Chinese to Chinese dictionary. So it has all the ideograms listed and a definition of that ideogram written in other ideograms. So this person cannot read the contents of this book. All they can do is scan for this symbol, and that symbol then has a definition. That definition is the definition of the word, but it also has some instructions. It says, if you see this particular squiggle, take another piece of paper and write these other squiggles instead. So it's basically a big if, then, else nested set of statements like Eliza. It's basically giving instructions to this person about what to do. If you see this symbol, write down these symbols. If you see that symbol, write down these other symbols. If you see this symbol followed by that symbol, write these other symbols. So you can imagine this is a pretty big book. Yeah? So this person diligently does what it says. I'm sorry, I misspoke. It's not all written in Chinese. It's a mixture of Chinese and English. The English says, if you see this symbol, write these other symbols. My apologies. Yeah? So it's if, then, else, written in a language the person understands, but there's no definition of the symbols themselves. The person doesn't know. They write all of these squiggles and then pass it back out through the door. So this whole Chinese room is basically acting like Eliza. right? Just a bunch of if, then, else statements. In theory, if this book is big enough, then the paper that comes back out of the room, the Chinese speakers should be able to read it and say, oh my God, what a profound, empathetic, deep response to the question that I asked. Whoever is in that room, not only do they understand Chinese, they are a deep, intelligent thinker. Searle said, this is a proof by contradiction that the Turing test doesn't work. The Chinese room passed the Turing test. It fooled these people into thinking there is a Chinese speaker inside the room, but there isn't a Chinese person inside the room. There is nothing inside the room that understands Chinese. So somebody might say the Chinese room is thinking or understands Chinese, but it's not. So you can have the Turing test is setting the bar too low. There are things that can pass the test that aren't thinking. We humans, we also pass the test. But whatever the bar is, we're passing some higher bar. We're different from this. We actually, assuming you understand Chinese, we actually understand Chinese. When somebody asks us a question in Chinese, if we understand Chinese, we think about it, we answer in Chinese. We understand Chinese. The room does not. Therefore, the Turing test is no good. Throw it away. We're out of time. Think on that. You have a quiz due at 11:59 p.m. We'll talk about your thoughts about the Chinese room next Tuesday morning. Have a good rest of your day.